we put the proposal in for this Newton Institute, the first reviews we got back were fairly positive. I don't know how to work this. But they said we had plenty of domain experts and we had some mathematicians, but we could improve the program by engaging more mathematicians. And Daryl was gracious enough to come on board and throw his weight behind the program. And we benefited greatly from that. And I'm excited that he's here.
I don't know how to click this.
Maybe you should just press enter.
Probably, yeah.
Okay.
I don't actually know what Daryl's going to talk about, and so I could read the title, but that won't do much, so I'll turn it over to Daryl. Thanks.
Thank you. So this is joint work with Cesare Tranchi, and it's about learning about what are multiscale fluid models and how to think about the interaction of the two layers. The basic idea for us, because we understand about climate and weather, is that we'll use the climate as the Lagrange coordinate for the weather. So we think of the weather as being swept around by some mean flow, and then we calculate it at the coarse scale and the fine scale. Okay, so this fellow began actually thinking about a birthday celebration for Julian Hunt, whose uncle was L.F. Richardson. So there's this big worlds and little worlds couplet. And the model proposes to answer the questions of how do the larger worlds affect the circulations of the smaller worlds? And how do the smaller scales participate in the interaction among the larger scales? Okay, and the answers are based on two key ideas. First of all, extending the idea of WKB into Fourier series decomposition of the velocity, and secondly, convection of the microstructure. You might see both of these as these were the ingredients that went into the derivation of the alpha model for turbulence some time ago, but it was a WKB, Lagrangian averaging. Here we'll do a Fourier series decomposition of the velocity and then apply a Lagrangian averaging, which is integrating over the fine scales, holding the coarse scales fixed, right? Because we're thinking of the coarse scales as the Lagrange coordinate for the fine scales. I'll try to explain what that means. Okay, big worlds, little worlds, what's a whirl? We go through the usual pictures that show whirls. Okay, there's some whirls, there's some computational whirls, and in a computation that was done a few years ago by Mark Taylor when he was at Los Alamos. And I'll not say anything more about this. This is a very rich picture. Here's some comparison of big whirls and little whirls with numerical resolution. Here's big whirls and little whirls in the ocean, looking at the sea surface height. Here's one of my favorite pictures of here's the big whirl and there's the little whirls inside. Okay, so we have some distribution of sizes, and there's this classic Google picture. Okay, so what I want to do is begin by just introducing this Fourier decomposition of the resolved and subgrid scale velocity. And I'm going to use the same decomposition as everyone does. It's the Fourier shells. I'm only going to have two shells. One set of coarse scales inside a sphere in K space, the other set outside the sphere. Okay, then, so we'll assume this idea here, which first came up in 1985 in a paper by McLaughlin, Papanikolaou, and Piranu, that the resolved scale flow is, well, they said that it was, they called it, what do they call it? Small scale advection. but it means the same thing. To me, it means that the resolved scale flow is a Lagrangian coordinate for the subgrid scale flow. So we'll obtain these kinematic multiscale equations and then start talking about how to put some physics into it. And along the way, and so we're not going to talk about viscosity today. We're going to just talk about the nonlinearity of the problem when you're doing averaging. And we'll derive a resolved scale closure model based on this advection law, and it outcomes the Mizrahi-Poland closure model from 1997, or a slight extension of it to make it self-consistent. And then we introduce a mechanism for multiscale backscattering, which is based on coupling the resolved scales to the slowly varying envelope of the fluctuating scale. So we're back to this WKB idea. Okay, any questions? Just ask questions as we go. Yeah.
Just want to clarify. Right. What we mean, the resolved scale flow is a Lagrangian coordinate for
Yeah.
subgrid scale flow.
Yeah.
Do you mean that like it's some kind of pushes the like what does that mean actually?
Yeah, I think it'll be explained in the next couple of slides. If it's not explained, ask me again. Okay. Basically, the Lagrangian coordinate that you usually think of is another Lagrangian coordinate, and the first flow gives you the other Lagrangian coordinate, and then you measure the small scale flow relative to that one. So there are two maps from Lagrange to Euler. There's one map from Lagrange to the coarse scales, and then the other map from the coarse scales to the fine scales. And we think of the second map as just like the first one, except you're at the coarse scale. You're moving with the coarse scale. Okay, so let's get started with this. So we can begin with this nice little decomposition. We're going to work in a periodic domain. And this is any periodic function u of x. So we think of a vector function that emits a Fourier series expansion on the unit cube may be decomposed into a sum of two periodic functions. Okay, so there are u1 of x1 and u2 of x1 and x2, in which u2 has zero mean when you integrate over x2. Well, okay. Actually, I think we all know this, right? You can decompose into Fourier, people make shell models with many layers of these decompositions. But let's just go through the calculation. So we Fourier decompose our function as a set of amplitudes inside a sphere and a set of amplitudes outside the sphere. We look at the sum, okay, and then we rewrite the vector k as k1 plus n k2, where n is our cutoff for the sphere, and then we recompute our expansion, rearrange, and when we've rearranged, then we have a sum over the outer scales of something which is summed on the inner scales. Okay, is that clear? Right, and this is a standard Fourier transform method for projection onto two sets of scales. So any periodic function can be rewritten as u1 plus u2, and we can if 1 over epsilon is in, then there it is, and then we can think of as these are the scales that are slow, and these are the fast or coarse and fine. And we write our decomposition, just call it x over epsilon x2. Okay, and x2 has zero mean. U2 has zero mean under integration over x2. Okay. Questions? Okay, so this is my point about the connection to WKB. WKB would expand the coarse scales and the fine scales into a mean and an oscillating part. And then in order to do the averaging, you'd average over this fast phase. Okay? So our expression here includes all the other phases. The usual problem with WKB is if you try to include another phase, it has resonances. But we just Fourier transform the whole function. It's not going to have any resonances. We've got the whole function. Okay, so that's what the beauty of Fourier transform does for you. Okay. So here's the main assumption. Here's the answer to your question. It's called the kinematic sweeping assumption. It's that while the Lagrangian label for the mean flow is taken to its current position by this map from the x1, 0 to x1, and then the fluctuation label transforms to the fine scale by a map like this map, except it's mapped from x1. Okay, so we're composing two Lagrange to Euler maps. Okay. You're not going to be surprised by this. Okay, because if we now apply that, we'll get the Euler equations at the coarse scale, divergence free, and because we have sweeping by u1, the time derivative for u2 will have two parts, u1.grad u2 and u2.grad u2. And ordinarily, when people do averaging, they throw away this nonlinear part. But we're going to keep that part, okay, so that u2 will have its own nonlinear Euler dynamics.
Wait a second, why isn't, I don't understand, you are somehow decomposing the U1 and the U2 arguments. Is that allowed? I mean, the U2 acts on the grad, the x1 gradient also.
Yes. Oh, u2.
Yeah.
There's a reason for that. I want. Yeah, because you're thinking of u1 plus u2
Yeah.
dot
Yeah.
grad 1 u2.
Yeah. Yeah.
Let me come back to that, okay? So I think what happens is that in the integration, okay. u1 dot grad, that's right. Okay, so what will happen in the integration is the other term will integrate to 0, okay? But that will hear it, actually. Yeah, no, that's a statement. I'll come back to this.
All right.
Okay, and I need it so that if u2 has 0 mean, then it keeps 0 mean. Okay, and if you average this equation, keeping that other term, then that'll average out. Okay, but yeah, that's a really good question. Right now I don't remember exactly why that went away, but I'll show you when we think about it from a variational principle that it doesn't come up. Okay, so maybe that's the point, is that, yeah, that is the point. We're just changing the time derivative when we do this moving into the frame. Okay, we're not doing an expansion. Okay, we're saying that, yeah, this is why it's not there. We're saying we want our solution, even though u2 does depend on x1 as well, we're defining our solution as having a time derivative, which is moving with u1 plus its nonlinear time derivative, and the what is the other one? u2 dot grad u1.
All the mixed ones.
What?
All the mixed ones.
Yeah, all the mixed ones.
Grad,
Yeah.
X1
So this is the statement of the model, that we're just going to change the time derivative of the small scales to be swept by the large scales. Right? That's the assumption.
That doesn't remove those terms.
Okay.
We can discuss it over coffee.
Yeah. No, you'll see it comes out nicely. And I think actually this slide also addresses that point. It's because we're doing the averaging. So here's the sum of the velocity squared as your kinetic energy, okay? But if you average this thing over x2, then the oscillations of the cross term disappear. Okay, and we're now going to use this as a Lagrangian in a second, and and all those other mixed terms that will be gone. Okay, so now we can take the square of a sum, average it, replace it as sum of squares, because we're integrating over x2 holding x1 fixed, which is like, this is like integrating over the fast phase holding the slow part of the solution fixed. Okay, so that's the point. And then the other point is that we go back to those equations. These two terms in the sum end for the kinetic energy are both conserved. Okay, so here's the geometrical derivation of this. So I want to take my Lagrangian, depending on U1 and U2, and I want to get some general equations. Okay, I want to get it by averaging in this Lagrangian. And so I define M1 to be the variation with respect to the first velocity, M2 to be the variation with the second velocity, and d by dt1 is our time derivative following U1. If we apply Hamilton's principle to this, we get these equations for M1, which for the kinetic energy Lagrangian by itself, this would be U1, and this would be U2, and this would be those equations that we just looked at. And this part would have disappeared because that would be a gradient that could be absorbed into P1 if M2 is U2. But in general, we can do our modeling in the Lagrangian, and we get a set of coupled equations for M1 and M2, which have two pressures, and these are determined by incompressibility. Okay, so this gives us the freedom, and what is happening when the when there's something more to the kinetic energy in the model than just the sum of the squares, then you get this feedback of the small scales into the large scales. All right, that's the trick here. And when M1 is U1, then we get back to the previous equations. U2 being dragged along by U1 and the other flow. So the set of equations that I showed you will conserve energy and follow from Hamilton's principle, and follow from an averaging procedure in Hamilton's principle over the x2 quantity. Okay. So I'm doing something slightly different from just putting in the decomposition into the equations. I'm putting the decomposition into the Lagrangian, and then I'm averaging, and then I'm taking the variation. I get those equations. Okay, so I'm not keeping everything. I am doing an average in the Lagrangian, and then I take the variations. And it's different from just putting in a decomposition. Right. Okay, so these equations actually have lots of structure to them, which is very nice. In particular, the subscale problems have subscale equation has singular vortex solutions. So you know how people doing models of turbulence often think about the turbulence as a set of vortices that's being carried around by the large-scale flow. Okay, this representation is part of this description, and here's the backscatter or Reynolds stress term back into the coarse flow. Okay, and these fluctuations, so this reduces the dimension of finding the multiscale problem because each of the vortex filaments is attached to the mean flow by the velocity relation. Okay, so the properties of this set of equations. First of all, the total circulation at each x1 is conserved. So it's the integral around the loop moving with velocity u2 of the m2 guy, holding x1 fixed. Okay, then take its time derivative, allowing x1 to move, and you get 0. Okay, also the total subgrid helicity is conserved. Okay, m2 dot curl m2. So we have these two conserved scalars, and we can make a vorticity-like vector B by taking the cross product of the two gradient quantities, because these scalars depend only on x1 and t1. Okay, so we want to represent what's happening at the subscale in terms of its properties, which are swept by the large scale. Okay, and we'll combine them into something that looks like vortices, because we know that we have these vortex solutions. Okay, and so what comes up because of these equations is then that this quantity B obeys Ortel's theorem and basically satisfies the divergence-free vorticity equation for B. So it acts like the vorticity, an additional vorticity in the coarse scale problem. Okay, so suppose the Lagrangian depends on U2 only through these quantities. Okay, then we put that into Hamilton's principle, and we derive the Reynolds stress in terms of the vector B. Okay, and B is advected by the coarse scale flow. Okay, if we say, well, if we put in just u squared minus b squared into our Lagrangian, just bare, we get exactly MHD. Okay, but turbulence is not MHD. Okay, but it tells us that we've reached the structure that we understand. Okay, turbulence is not MHD, so we're going to put in this constraint that B is advected like a magnetic field, but we think of it now as a vector which has a constant length, called the length 1. And we impose it with another Lagrange multiplier, Q. Okay, and Q then appears in the force that comes from the Hamilton's principle with this Lagrangian. And so there's a total force, there's two pressures, and this other stress tensor object. And the B equation still has these properties it had before, but now this is where F comes in to the next derivative in this Okatani relation. And given F in this form, taking its gradient and contracting with the B's, summing with B dot the gradient of U1 squared is what you need to solve in order to find Q. And Q then obeys this Monge-Ampere equation. Okay, so if we go back to this multiscale idea, I don't think I really said what I wanted to say here because, yeah, I missed this point here. These equations with this particular stress tensor and a different way of computing Q are the Misra and Poland turbulence model, number 2. Okay, so that's another connection of this theory to things that we know about. And that model's been around for quite a while and it's been tested a lot. Okay, so now what I want to do is do some kind of alpha model but with feedback. So I want my Lagrangian to be the kinetic energy for the coarse flow plus the kinetic energy for the fine flow plus a coupling term which involves the coarse gradient of U2, right? So here's where it first comes in. Okay, so if you put that in, then what you'll get, Hamilton's principle will give you this for your Reynolds stress, It'll give you this for your evolution of M2, which is now Helmholtz operator on U2. And it will give you a transport velocity at small scales, which is nonlinear. There's a nonlinear, non-local term. And U2 is smoother than M2 by inverting a Helmholtz operator. So it's a filter with this width alpha 1 in it. Okay. And if you look, if there weren't for the x2 derivatives, I mean integrations, and the two components, it was just the divergence of grad 1 u1 dot grad transpose dot grad 2 u2 or u1, sorry, 1 1 1 1, with no integration. That's Tony Leonard's model, okay, for tensor diffusivity. So this is another connection that this idea makes to the literature. And it's a simple idea. I think it's an idea that all you guys can start thinking about implementing your own way. But it's an important point. The derivation has been gotten by averaging a Lagrangian, not by doing an expansion. When you average the Lagrangian, you keep the properties of the original equation, like energy conservation and circulation and helicity. Okay, right, one last connection. If we go back and we write our singular subgrid scale vortex solution as a delta function times a amplitude that's depending on x1, and this integration, we're integrating over s, it's going to remove a dimension from the problem. U2 is gotten from R by taking the sweeping time derivative. If we then can rewrite the Reynolds stress in a vortex representation in terms of R prime here, which is R evaluated at x1. And now, when you look at this and put this into the Reynolds stress, this thing is very close now to this Pullen-Saffman-Lundgren theory of dragging a bundle of vortices around as a turbulence model. Okay, so this talk, we're laying out a strategy for multiscale modeling. Okay, it's convected subgrid scale microstructure using Hamilton's principle. Okay, so we identify the x1 advective properties of the subgrid flow as x2 integrated subgrid circulation and K and H. Okay, this leads to a reformulation of well-known models in turbulence and unifies them, right? It unifies the viewpoint for them. It actually doesn't deliver exactly what they are because they're not quite as consistent as you get from a variational principle, but it delivers the corrections to them, which provide back the properties of the solution that the original equations had. And if you use this multiscale coupling and look at the the coupling of the velocity of the envelope of the velocity fluctuations to the gradients of the slowly varying part of the U2, you get this Reynolds stress, and that Reynolds stress is exactly in the same shape, grad U transpose dot grad U, as Tony Leonard's model, but it's giving you some impact of the x2 dependence on the fluctuating velocity, averaged. So this would be written as a bar of a product, not a product of bars. Okay. So thank you very much. That's okay. Yeah, thanks for listening. This is a message.
Yes. Before we jump into questions, This room is not so great for discussion, at least not nearly as good as the seminar two, which is a lot tighter. So speak up, project, so that we keep all included in the discussion. Peter?
So do I understand correctly that you keep identity of your large-scale climatic Lagrangian coordinates? They don't change, right?
Yes.
So there is an assumption that there is a well-defined steady climate that doesn't change.
No, it's not steady. No, it's
Well-
moving. It's also changing with time, and it's this, yeah, and it's the same time variable, okay? But one is a coarse scale, and the other one's a fine scale.
I think the assumption there is that there's a well-defined scale separation between
Yeah.
X1 and X2. That's the,
Well, yeah, you know how this works. If this scale, if you don't identify in your data some scale separation, then you have to have more shells, and this becomes multi-scale with different physics at different levels. Okay, this is just an attempt to put together something that's connected to what people know and which might be computable.
Has there been attempts to compute with this in this frame?
People claim they will. Yeah, people claim they will, and they haven't done it yet. It's brand new, okay? It's just been here since August or July, just arrived. And its connection to the other turbulence models, the alpha model, the Misra-Pullen model, the Lundgren model, the Leonard model, bodes well for, it being in a domain where people have, sort of believe that things are happening like this. Because you can always go to the other model if that's their favorite model by just erasing one of the terms. Or erasing an integral over x2 and just treating it as a function of x1, you get the tensor diffusivity model, which many people like.
What is the principle to divide things to two space? I mean, the U1 and U2. How to divide that? Or things are all correct?
If you look in your data, and you can see a scale separation, like, we looked at the whirls and the big whirls and the little whirls, okay? Then you can make the scale separation. Your data is making it for you. If you're looking at a computer calculation for turbulence, then you're going to see a continuous range of scales, okay? On the other hand, there are many models, like shell models, which do exactly this decomposition, but they don't keep as much PDE stuff. The shell models are ODEs. So, yeah, I guess the answer is you need to be lucky, and it's possible that you're lucky if you're trying to understand the effects of climate carrying weather.
So it depends on different situation.
I don't hear you.
I mean, things depend on what we want to do.
Yeah,
And then
always,
do it.
always. When you're modeling, that always is true. Yeah.
In that same context, you mentioned Julian Hunt at the beginning of the
Yeah.
lecture, and I know that Julian and Christos Vasilikos had that paper, I don't know when it was, in the 80s, where they showed that if you take a vortex, a 2D vortex that is a exact solution of Navier-Stokes, they could cook this up in a JFM paper, and you analyze it spectrally, out pops k to the minus 5/3, which was a statement that they made, which I find very intriguing and not much followed up. What they said is, you don't need activity on all scales to get the spectra we see in turbulence data. You just need a collection of singularities that have the right scaling. And this would actually, if that was true, it would very much support what you're doing. Because then you could claim, well, it might be true that we can't see scale separations in the spectrum, but if we look at the data, and maybe Mark's simulation data reveal that if you look at them in the right way, we have collections of very concentrated stuff. and the environment is much smoother than the concentrated stuff. That would be a strong support for what you have.
Yeah, what I'm hoping for is that this alpha 1 term in the last model, I'm hoping that, yeah, if we put that, if that term is small, then we get k to the minus 5/3, spectrum. Because, it has a lot of good features for that possibility. And if it's alpha is, say, twice the grid scale in a computation, it'll turn the spectrum down so that it'll stop the madness of going to smaller and smaller scales. So thanks about that. And I will say, when you first started talking about this, was it a single vortex that had the k to the minus 5/3?
I think so.
Yeah. Well, actually, I mean, the Lundgren model, of a lattice of vortices also gets k to the minus 5/3. Yeah, I think there's a lot of connection when you have fields of vortex filaments getting k to the minus 5/3, and this amounts to dragging them around with another flow.
We're just following up on this k to the minus 5/3. In my simulations of the atmosphere at 2.5 kilometer resolution, I produce actually quite nice 5/3 spectra. And what I observe is a sort of an equipartition for a very large span of wave numbers between vortical and divergent motion. Is that consistent with your...
Between vertical and potential flow?
Like if I basically split the kinetic energy,
Yeah.
in a spectrum model, you have the vorticity and the divergence, so I look
Yeah.
at the two contributions separately.
Okay.
And they're pretty much, divergence is slightly lower, but there's certainly no crossover in the two.
I
so
see,
they basically
yeah.
follow over the whole 5/3 spectrum each other, essentially. For we can say between wave number 300 in the atmosphere to wave number 3,000 plus.
This is a hydrostatic model, and the divergence.
No,
is
it's not
horizontal.
hydrostatic. It's a non-hydrostatic model, and I talk about horizontal divergence.
Horizontal
Yeah.
divergence, right.
Yeah, so,
But it's a non-hydrostatic one.
yeah,
And I
this-
was just wondering if there anything in your theory would sort of kind of because some people would argue that divergence is more dominant basically as you go to smaller scales.
yeah,
But that doesn't seem to happen in my simulation, so I was just wondering.
yeah. When you were mentioning your results, my first thought was, this is how you make a balance model. Okay, you would decompose the flow into a curl and a gradient, and the gradient, and it's a 3D gradient, and the gradient is multiplied by Rossby number. Okay, so it's taken to be the next term in the expansion. And the balance models just have a way of working really pretty well. And my first thought was, this is another one of those occasions in which the balance model works, and it's pretty hard to figure out why. And that was my first thought about it. I think it's encouraging, and it might be possible then that what you would. See, it's like what you're saying is kind of the opposite of what we were just talking about a moment ago, right? Because your subgrid scale quantities, your small quantities, would have no vorticity, right? They have a divergence but no vorticity.
Wait a second, he's only talking about the horizontal divergence. So
Yeah, okay.
The full 3D divergence,
Oh,
which I
okay.
think makes a big difference.
Yeah, I'm sure it does. Yeah.
Yeah.
Okay.
Yeah, I wanted to talk about horizontal.
Yeah, maybe we should talk some more about that. Thanks. More questions?
Maybe one, Stefan? Last question?
Yeah, maybe. Do you think you could use, it looks like you could use things like wavelets, for example, to get the scale separation, to build a model which actually implements the feedback term?
Yeah. This is just the simplest decomposition. If you find a decomposition that seems to be working for your data, you should use that one. And put it into a variational principle under the assumption that the small scales are being swept by the large scales. Take the average, take the variation, you get new equations, and those equations have these properties. They have a Kelvin theorem. They have helicity conservation. They have the things that the original Euler equation started with. After you've built all this thing, right, well, then you have to talk about viscosity. But you're doing things separately. You don't have to, you won't be wanting to now double count by putting in transport into your viscosity. You then want a viscosity tensor which is symmetric. You don't want to have one that's causing flow, things like that. Yeah, and I believe we should do the modeling and the nonlinearity first. And I believe that asymptotic expansions don't preserve the properties you want to keep, but decompositions and averaging do. Thanks.
On that, quick.
I have one more question regarding your statement on the backscatter. Is your statement contrary to the efforts of introducing stochastic backscatter?
Yeah, okay, so I thought about that when I put that word backscatter in. And if I were modeling the subgrid scale, and I put it in for a reason too, because if I were modeling the subgrid scale as a stochastic process, it's possible to get terms that modify the nonlinearity in the term in the equation for the coarse scale. Okay, that's what this says, and that's also what Chuck Leith did. He put the backscattering in the way that would go back and modify the coarse scales. Yeah, so I think I said that because I was thinking about, and I'm working on some stochastic modeling and trying to figure out when does a stochastic process in a fluid problem do backscatter and when does it just introduce viscosity or diffusion. And it's actually, Chuck Leith's idea was so good, but it's actually hard to find a stochastic process that won't just give you diffusion. If you put in a Brownian motion, a Gaussian, the stochastic process, it seems like it can only give you diffusion, but I'm looking for a backscatter interaction with the coarse scales.
Okay, well, let's thank Darryl again.